Good evening, everyone. I'm Lucrezia Contiero, a second-year PhD student at the University of Padua, and today I will show you some results in terms of fatigue strength of gas metal arc-welded joints made of 316 low-carbon austenitic stainless steel that include an AM part. An AM part because, as we all know, additive manufacturing is extraordinarily growing in industrial sectors. Among them, it is worth mentioning the amusement park industry. Here, for example, if we focus on the wheel system of a roller coaster, we can assume to overcome one of the traditional solutions by taking advantage of the EM capability for the complexity for free, by producing this part through EM and then joining it with the traditional manufactured one through welding. In this way, we obtain a so-called dissimilar welded joints that is dissimilar because of the different microstructure of the two welded parts. Another example can be found in a structure like this. Here, if we focus, for example, on a seat, we can assume to produce different parts through AM and then joining them together, obtaining an homogeneous welded joint. But as we all know, structures like these are often subjected to cyclic loads, and this means that we need a fatigue design of these joints. But if we refer to traditionally manufactured welded joints, we know that the most critical point is represented by the welded toe due to the notch effect. In this case, where we have also an AM part, we need to take into account also the possible presence of defects due to the manufacturing process. In addition, when we talk about traditionally manufactured welded joints, we have standards, for example, the Eurocode 3, which provide the specific the design curve, each one for a specific joint geometry and specific loading condition. However, if we talk about joints with the EM part, at the moment, there are no standards. In addition, we refer to complex joint geometry and complex loading condition, and that's why a local approach is needed. The local approach that now I briefly show you, and that is the method that I apply also to reanalyze my fatigue data, is the Pixar's method. The Pixar's method is a method developed in Padua, which is based on the assumption that the welded toe of a welded joint can be assumed like a sharp V-notch. In this way, with a finite element analysis with a coarse mesh, we can estimate the MCFA to the welded toe, and then by assuming the mean strain energy density as a failure criterion, we can rewrite this expression in terms of an equivalent peak stress, and so we can use this equivalent peak stress to estimate the fatigue strength of our joints. Now that I briefly introduced you in the topic, I move to the main topic of my presentation, which is the experimental characterization both of traditionally manufactured welded joints and joints with an AM part. We test butt welded joints with a thickness of 8 millimeters. We acquire from the datasheet the chemical composition of our joints, and we also carried on some static tests in order to acquire the mechanical properties of our joints. We also monitor the manufacturing process, and so talking about traditionally manufactured welded joints, they are produced of hot rolled plate. On the case of joints with an AM part, we have the plate with this building direction, and this is the building direction that we can find here in the specimen. Then we weld the two plates with the 3 passes, and finally cut them through ADM, obtaining these final shapes. We also carried on an extensive geometrical analysis, focusing specifically on the weld bed by measuring all the main parameters, that means the opening angle, the H, and the width of the weld bed, both for the top side of the specimen and also for the bottom side of the specimen. And here you can see the mean values that we acquire. We also analyze the misalignment of our specimen, and as you can see in this case, they are negligible. We also carried on some tests with the strain gauge spacemen in order to be sure that the bending induced by this misalignment was negligible, and it was. And also we verified that the loading ratio that we can measure with the strain gauges was the same that we assumed to apply, that was the theoretical one. We also carried on this characterization also for the joints with the AM part, so acquire all the measurement of the different parameters. And as you can see, the mean values are almost the same of the traditionally manufactured welded joints. On the case of the misalignment, as you can see, they are greater, and this induces us to mill the gripping surface. Then we also measure, also in this case, we have some tests with the strain gauge spacemen, and we verified that the bending at the failure point was negligible, also in this case, and that the loading ratio that we can measure with the strain gauges was the same of the theoretical one. We performed the test with a servo-hydraulic machine by applying a pure axial loading condition with the loading ratio almost equal to 0. And here you can see the result. This is the first series, the traditionally manufactured welded joints. And here the red line is the design curve provided by the Eurocode 3. As you can see, the data differs in terms of the inverse slope, which is higher, and also the fatigue strength at 2 million cycles. So a fatigue design at a higher number of cycles, which refers to this design curve, will induce an oversize of the component. By focusing specifically on some joints, for example, a joint that has been tested in a high-low level, we can observe that failure occurs at the weld toe, specifically the most critical one due to the notch effect, and that propagate along the interface. And the same, we observe a joint test in a low-level condition. We observe also in this case failure at the welded toe and the propagation along it. Focusing on the fracture surface, we observe in the high-low level test spacemen a multiple fatigue crack initiation point, almost equally distributed along the spacemen thickness, and finally the plastic zone due to static failure. Focusing on the fracture surface of a low-level test spaceman, we observe the main fracture initiation point from this side, and only probably secondary starting point in this zone. Then here you can see also the data about joints with the NAM part. And as you can see, they are in good agreement with the fatigue strength of the traditionally manufactured joints. And also in this case, they exhibit an inverse slope that is higher of the one provided by the Eurocode 3. Almost all failure occur at the weld toe in on the AM side, and only one failure occur at the weld toe in the on the broth side, so the traditionally manufactured part. And the failure occur at the weld toe, the most critical one due to the notch effect, and propagate as in the traditionally manufactured welded joints in the interface. Focusing on the surface, fracture surface for a medium, high, low level test spaceman, we observe that failure starts from this point, the fracture initiates from here and then propagate in this direction. Then for a joint tested in a low level condition, also in this case, failure occur at the weld toe, the most critical one due to the notch effect, and due to a lack of penetration, we also have a starting crack also from this side. Analyzing fracture surface, the fracture initiates from this point and then propagate in these directions. So comparing broth growth and additive growth welded joints for almost a high-low level condition, we observe the main difference is in terms of the different roughness of the surfaces. Here we have multiple fatigue crack initiation point. On the contrary, here we have one main starting point. Focusing on low-level test spacemen, also in this case we have different roughness. Here we have one main fatigue crack initiation point and only limited secondary starting point, while here we have only one fatigue crack initiation point. All this data have been finally reanalyzed with the local approach, and here you can see them reported in terms of an equivalent peak stress. As say before, the data of additive welded joints are in good agreement with the traditionally manufactured ones. However, if compared with this scatter band, which has been defined for structural steel joints, they are not in good agreement in terms of the inverse slope. Then we also compare our data with the ones taken from literature, both in terms of the nominal stress and in terms of an equivalent peak stress. As you can see, they are in good agreement with the literature data. And also we compare our data with this curve and this scatter band defined for austenitic stainless steel, but traditionally manufactured welded joints. And as you can see, also in this case, they are in good agreement with this new curve and scatter band. And so to conclude, we test butt welded joints, both traditionally manufactured ones and joints with an AM part in a pure axial loading condition with the loading ratio almost equal to 0. We observed that failure occur at the welded toe due to the notch effect, also in the case of joints with an AM part. And in this case, failure occur at the welded toe on the AM side. We observed that the fatigue strength of joints with an AM part is similar to the ones of joints that are traditionally manufactured, but it differs from the prediction of the Eurocode 3 curve. However, our data are in good agreement with the literature's one and also with a design curve and a design scatter band defined for austenitic stainless steel traditionally manufactured welded joints. As future development, we are going to test other spacemen of this geometry, so butt welded joints, and we are going also to test other joint geometries in also to validate these findings also for other geometries. And that's all for me, and thank you for your attention. If you have any question, I'm happy to answer.